I want to begin with a simple observation about curiosity. It is the quiet engine behind every meaningful advance we make as a species. Between that opening thought and what we choose to understand next lies a vast landscape shaped by patterns, structures, and questions that refuse to stay neatly separated. When we look closely at the universe, we discover that its deepest laws are not merely written in equations but hinted at through symmetry, geometry, and an almost unreasonable coherence. Mathematics, in this sense, is not just a human invention for bookkeeping. It behaves more like a realm we gradually uncover, one that was already there before we learned how to describe. Consider how abstract ideas, formed with no practical goal in mind, repeatedly turn out to illuminate physical reality. Concepts developed in the quiet corners of thought often resurface decades later as the backbone of our most precise theories. This is not coincidence. It suggests that the universe itself is structured in a way that resonates with deep mathematical truth, and that our minds, somehow, are capable of tuning into that structure. The effectiveness of such abstract reasoning hints that reality may be far less arbitrary than it appears. Yet there is a puzzle here. While the physical world seems to follow elegant mathematical principles, our conscious experience of it does not fit so comfortably into that framework. Awareness, understanding, and insight feel different in kind from particles and fields. They possess qualities that resist reduction to computation alone. If our thinking were nothing more than a complex machine executing rules, it would be hard to explain how genuine understanding arises, or why new ideas can appear that are not obvious consequences of previous ones. This tension invites us to rethink the boundaries we draw between mind, mathematics, and physics. Perhaps consciousness is not an accidental byproduct, but a fundamental feature that interacts with the mathematical structure of the universe in ways we do not yet grasp. Progress, then, may depend less on faster machines and more on deeper conceptual shifts, on questioning assumptions so basic that we rarely notice them. History shows that major breakthroughs come from such shifts. They arise when we abandon comfortable frameworks and allow unfamiliar ideas to reshape our perspective. This process is rarely smooth. It often feels unsettling, even misguided, at first. But it is precisely this discomfort that signals we are approaching something genuinely new. In the end, our task is not merely to accumulate facts, but to seek coherence across domains that seem unrelated. By remaining open to unexpected connections, we keep alive the possibility that understanding the universe may also mean understanding ourselves a little better, and that is a journey still very much in progress. Curiosity is not a loud or dramatic force. It rarely announces itself with certainty or confidence. It begins instead as a quiet unease, a sense that what we see cannot be the whole story. This subtle discomfort pushes the mind to look beyond accepted explanations and to question ideas that seem settled. Without this impulse, knowledge becomes static, and understanding turns into repetition rather than discovery. Every genuine step forward starts with someone noticing that the familiar no longer feels sufficient. What makes curiosity so powerful is that it does not demand immediate usefulness. It allows ideas to exist before they are justified by application or reward. Many of the concepts that later transformed science and technology were once regarded as abstract diversions, pursued only because they were intellectually compelling. Curiosity gives permission to explore such paths without knowing where they lead, trusting that coherence and meaning may emerge later. This freedom is essential, because progress rarely follows a straight or predictable route. At a deeper level, curiosity reflects a belief that reality is intelligible, that beneath complexity there is order waiting to be understood. When we ask questions, we implicitly assume that answers exist, even if they lie far beyond our current reach. This assumption has guided human inquiry across centuries, encouraging the development of new languages of thought, capable of capturing subtler aspects of the world. Each new question refines the way we think, shaping the tools with which we investigate further mysteries. Curiosity also demands intellectual humility. To ask a question honestly is to admit ignorance, to recognize the limits of one's understanding. This humility is not a weakness but a strength, because it keeps the mind flexible and receptive. Rigid certainty closes doors, curiosity opens them. By remaining aware of how much we do not know, we preserve the ability to revise our beliefs when confronted with new evidence or deeper insight. Importantly, curiosity is not confined to collecting facts. It seeks connections, patterns, and explanations that unify diverse observations. A curious mind looks for coherence rather than accumulation, aiming to see how different pieces fit together into a larger whole. This integrative drive has repeatedly led to breakthroughs that reshape entire fields, revealing that problems once thought separate are in fact deeply related. Finally, curiosity is what sustains long-term progress. Motivation driven solely by immediate results tends to fade when obstacles arise. Curiosity, however, persists because it is fueled by wonder rather than reward. It keeps inquiry alive during periods of uncertainty when answers are scarce and effort seems disproportionate to outcome. In this way, curiosity acts as the silent engine of advancement, continually pushing human understanding forward, even when the destination remains unknown. When we reflect on mathematics, it is tempting to regard it as a sophisticated tool created by human minds to organize experience. Yet, this view becomes increasingly difficult to sustain when we observe how mathematical structures, developed in complete abstraction, later turn out to describe the physical world with astonishing precision. Equations conceived without any experimental motivation often reappear as the natural language of fundamental laws, as if they had been patiently waiting to be recognized. This recurring pattern suggests that mathematics possesses a form of existence that does not depend on our invention, but on our discovery. The sense of discovery arises from the way mathematical truths constrain us. We do not decide whether a theorem is true in the way we choose a convention or a definition. Once the basic axioms are accepted, the consequences unfold with an inevitability that feels external to us. Mathematicians speak of being guided, even surprised, by results that seem to emerge from the internal logic of the subject itself. This experience is hard to reconcile with the idea that mathematics is merely a human-made construct, shaped entirely by culture or convenience. Moreover, the internal consistency and richness of mathematics point toward an underlying structure of remarkable depth. Different branches, often developed independently, repeatedly intersect in unexpected ways. Techniques designed for one purpose suddenly illuminate problems in distant areas, revealing a hidden unity beneath apparent diversity. Such interconnections give the impression of an objective landscape that we explore from multiple directions, rather than a collection of arbitrary systems assembled at will. The relationship between mathematics and physical reality strengthens this impression. Nature appears to select particular mathematical forms, favoring simplicity and elegance over complexity. Physical laws often correspond to minimal principles, symmetries, or geometric constraints that seem almost aesthetically motivated. It is difficult to believe that the universe should align closely with abstract reasoning unless both are grounded in a common underlying order. This alignment challenges the assumption that mathematics is merely a convenient descriptive framework. Our ability to access this realm of abstract truth also raises profound questions about the nature of human understanding. The mind seems capable of grasping concepts that have no direct sensory counterpart, yet correspond with striking accuracy to the behavior of the physical world. This suggests that cognition is somehow attuned to deep structural features of reality. The effectiveness of mathematical reasoning may therefore reflect not just the power of formal logic, but a deeper resonance between thought and the fabric of the universe. Seen in this light, mathematics becomes more than a language. It becomes a window into what exists. To engage with it is to participate in a process of uncovering truths that were already there, independent of our awareness. Each new insight expands the territory of what is known, reinforcing the idea that mathematics is not brought into being by us, but patiently revealed through sustained and disciplined curiosity. At first glance, the universe appears chaotic, filled with irregular motion, randomness, and complexity that defy simple description. Yet as observation deepens, a striking order begins to emerge beneath this apparent disorder. Repeatedly, The same patterns reveal themselves across vastly different scales, from the delicate structure of atomic interactions to the grand architecture of galaxies. This persistence of form suggests that chaos is often only superficial, masking a deeper coherence that governs how things unfold. Symmetry plays a central role in this hidden order. It is not merely an aesthetic feature, but a guiding principle that shapes physical law. When a system remains unchanged under certain transformations, those invariances impose strict constraints on its behavior. Such constraints are not imposed from the outside, they arise naturally from the structure of the system itself. The laws that emerge from these symmetries often possess a simplicity that contrasts sharply with the complexity of the phenomena they generate. Geometry provides another window into this coherence. Space and time are not passive stages upon which events occur, but active participants whose structure influences motion, energy, and causality. The curvature of space, the relationships between dimensions, and the topology of underlying frameworks all contribute to how physical processes evolve. Through geometric insight, relationships that once seemed unrelated become unified within a single conceptual picture. What is particularly striking is that these ordered principles often manifest as mathematical inevitabilities rather than empirical accidents. Once certain conditions are in place, the resulting behavior follows with necessity, as though the universe has little choice in how it behaves. This sense of inevitability challenges the view that the laws of nature are arbitrary or contingent, instead pointing toward a framework where consistency and harmony are fundamental. Even randomness, when examined closely, tends to reveal structure. Statistical regularities emerge from large collections of seemingly unpredictable events, producing stable patterns that can be precisely described. These regularities do not eliminate uncertainty, but they constrain it, ensuring that unpredictability operates within well-defined boundaries. In this way, order and randomness coexist, each shaping the other in subtle ways. The recognition of such coherence reshapes our understanding of reality. It encourages the belief that deeper explanations remain to be found, even when phenomena appear irreducibly complex. By searching for underlying patterns, rather than settling for surface descriptions, inquiry moves closer to the principles that unify diverse aspects of the world. The universe, viewed through this lens, is not a collection of isolated facts, but an interconnected whole, governed by structures that invite continued exploration and deeper understanding. Among the most persistent challenges to our understanding of reality is the nature of conscious experience. While physical theories have achieved extraordinary success in describing the behavior of matter and energy, they remain curiously silent on the question of subjective awareness. We can map neural activity, measure electrical signals, and simulate increasingly complex processes. Yet none of these descriptions seem to capture what it actually means to experience a thought, a sensation, or an insight. There remains a gap between objective explanation and lived experience that cannot be ignored. A common assumption is that consciousness will eventually be explained as a form of computation, arising from sufficiently intricate information processing. However, this view encounters serious difficulties. Computation, by its nature, is syntactic rather than semantic. It manipulates symbols according to rules, but does not understand what those symbols mean. Genuine understanding, by contrast, involves insight, interpretation, and the grasp of truth. It is not obvious how such qualities could emerge solely from rule-following procedures, no matter how complex. This becomes particularly evident when considering mathematical understanding. When a person recognizes the truth of a mathematical statement, the recognition feels immediate and compelling, not the result of blind calculation. Insight often arrives as a unified realization rather than as the endpoint of an algorithmic process. This suggests that human understanding may involve non-computational elements, operating in ways that are not fully captured by current models of cognition. Neuroscience provides invaluable correlations between brain activity and conscious states, but correlation alone does not constitute explanation. Knowing which neurons fire during an experience does not tell us why that experience has the qualitative character it does, or why there is experience at all, rather than mere mechanical response. The explanatory gap remains even as data accumulates. This indicates that something fundamental may be missing from the prevailing framework if consciousness cannot be fully reduced to existing physical descriptions. It may point toward new principles that extend beyond current theory. Such principles would not undermine physics but rather complement it, much as earlier revolutions expanded our understanding without discarding what came before. The difficulty lies in identifying where such extensions should occur and how they might be tested. The mystery of consciousness therefore challenges us to reconsider deeply held assumptions about the nature of reality. It suggests that the universe may contain aspects that are not exhausted by physical structure alone, and that understanding may require a synthesis of ideas that presently lie apart. Rather than being an anomaly to be explained away, consciousness may be a clue, pointing toward a richer and more complete picture of the world than we currently possess. In periods of rapid technological advancement, it is tempting to believe that progress is primarily a matter of building faster machines and collecting larger quantities of data. While such developments undeniably extend our capabilities, they do not, by themselves, guarantee deeper understanding. History repeatedly shows that transformative advances arise not from incremental improvements in technique, but from radical shifts in the way problems are conceived. Without changes in perspective, increased power often serves only to reinforce existing limitations. Conceptual frameworks act as lenses through which we interpret observation. They determine which questions are considered meaningful and which possibilities are ignored. When a framework becomes entrenched, it can quietly constrain thought, making certain assumptions appear self-evident, even when they are not. In such cases, anomalies are treated as inconveniences rather than as opportunities for insight. Progress stalls not because data is lacking, but because interpretation has become rigid. The most significant breakthroughs occur when these frameworks are challenged. Such challenges often originate from simple but unsettling questions that expose hidden assumptions. These questions do not always arise from new experimental results. Sometimes they emerge from internal inconsistencies or conceptual unease. By confronting these tensions directly, thinkers open the door to new modes of explanation that were previously inaccessible. Technological tools can assist in this process, but they cannot substitute for it. A powerful machine can process information more efficiently, yet it operates within the conceptual boundaries set by its designers. If those boundaries are flawed or incomplete, the output will reflect those limitations. True innovation, therefore, depends on the capacity to rethink foundational ideas, not merely to automate existing ones. Conceptual revolutions are often resisted because they disrupt established understanding. They demand the abandonment of familiar intuitions and the acceptance of counterintuitive principles. This resistance is natural, but it can delay progress when adherence to tradition outweighs openness to revision. The history of science is marked by such moments of tension, where old and new views coexist uneasily before a deeper synthesis emerges. Ultimately, advancement requires a balance between technical skill and philosophical reflection. Tools expand what we can do, but ideas determine what we can see. By cultivating the willingness to question foundational assumptions, inquiry remains dynamic rather than complacent. Progress, in its most profound sense, is not measured by speed or scale, but by the depth of understanding, achieved through courageous shifts in thought. The pursuit of understanding has long been divided into distinct domains, each with its own methods, languages, and standards of explanation. Physics seeks lawful regularities in the external world. Mathematics explores abstract structures with internal necessity, and the study of mind grapples with experience and meaning. Treated in isolation, each domain achieves partial success, yet persistent questions arise precisely at their boundaries. These questions suggest that the divisions we rely on may be more practical than fundamental. Mathematics occupies a peculiar position in this landscape. It is accessed through thought, yet it describes the physical world with uncanny accuracy. This dual role hints at a deeper connection between mental activity and objective structure. When mathematical insight aligns with physical law, it becomes difficult to maintain a strict separation between the realm of ideas and the realm of matter. Instead, it appears that both may be manifestations of a shared underlying order that expose hidden assumptions. These questions do not always arise from new experimental results. Sometimes, they emerge from internal inconsistencies or conceptual unease. By confronting these tensions directly, thinkers open the door to new modes of explanation that were previously inaccessible. Technological tools can assist in this process, but they cannot substitute for it. A powerful machine can process information more efficiently, yet it operates within the conceptual boundaries set by its designers. If those boundaries are flawed or incomplete, the output will reflect those limitations. True innovation, therefore, depends on the capacity to rethink foundational ideas, not merely to automate existing ones. Conceptual revolutions are often resisted because they disrupt established understanding. They demand the abandonment of familiar intuitions and the acceptance of counterintuitive principles. This resistance is natural, but it can delay progress when adherence to tradition outweighs openness to revision. The history of science is marked by such moments of tension, where old and new views coexist uneasily before a deeper synthesis emerges. Ultimately, advancement requires a balance between technical skill and philosophical reflection. Tools expand what we can do, but ideas determine what we can see. By cultivating the willingness to question foundational assumptions, inquiry remains dynamic rather than complacent. Progress, in its most profound sense, is not measured by speed or scale, but by the depth of understanding, achieved through courageous shifts in thought. The pursuit of understanding has long been divided into distinct domains, each with its own methods, languages, and standards of explanation. Physics seeks lawful regularities in the external world. Mathematics explores abstract structures with internal necessity, and the study of mind grapples with experience and meaning. Treated in isolation, each domain achieves partial success, yet persistent questions arise precisely at their boundaries. These questions suggest that the divisions we rely on may be more practical than fundamental. Mathematics occupies a peculiar position in this landscape. It is accessed through thought, yet it describes the physical world with uncanny accuracy. This dual role hints at a deeper connection between mental activity and objective structure. When mathematical insight aligns with physical law, it becomes difficult to maintain a strict separation between the realm of ideas and the realm of matter. Instead, it appears that both may be manifestations of a shared underlying order.